Okay, let's go ahead and get started. Let's see, a couple comments about the problem set. I know a number of you spent a fair amount of time on it and I think had some frustrations with it. I guess I'll say that then sometimes struggles are a pain in the ass and sometimes struggles lead to something useful, and I hope that hope for most of you that it was more in the latter case than the former. There were a number of themes I thought in those problems 3 and 4 that I think will come up in future problems that you face. They come up all the time for me and when I'm doing my own work, and I think relate to some of the other things that we've talked about in the course. So some of the, I mean, problem 3 may be related to sort of content in other courses as well, of course. But some of the things that I think some of the continuing things that you have to sort of struggle with when you're working through problems like this, where you're doing some computation, but in the context of a statistical problem. In problem 3, you're sort of dealing with notation and wrapping your head around the notation, thinking about what sort of conditioning is going on in a given problem, and then the aspect of sort of recognizing that as you work through a problem, like, oh, this sort of looks like this other kind of problem that I know something about, like least squares, as you saw in that problem. And then in problem number 4, this notion of trying to wrap your head around sort of how do I explore this space that I'm having a hard time getting a handle on the scaling of the space or where the modes are and those sorts of things. And the fact that while you're trying to do that, you're also potentially debugging your code, and you may be that you're having trouble exploring the space because you've got bugs in your code. So that's of course something that comes up all the time. And then sort of issues of scaling and rescaling and reparameterizing. And then, as a number of you encountered, sort of some of the numerical issues that also came up in terms of the matrix computations. So all of these things are themes that many of you will run across again in the future. Okay, so let's go back to graphics. So we saw one example last time where we were sort of critiquing this graphic that was on the web, and I think we saw a number of interesting things and some interesting themes that came out of that. In the class notes, I also have a link to this paper from a journal called the American Statistician in 1984. So it's a very old paper, but I think it's worth looking at just to see some of the examples that they show, or that he shows, in terms of some of these graphics. So the graphics sort of look old because they were typeset in 1984, but I think a lot of the things that he points out in these graphs are still good principles to think about when you're developing your own graphics, and are sort of the root of a number of the bullet points I have here in the third page of the unit. So I thought we could look at some of these just to see what were some of the things that he was pointing out. So this is one example. This is something about achievement in class or in school for people of different ages. I know it's maybe a little bit hard to see the type size from there. But one of the points here is just this notion that in general we want to try and put a lot of information into a graph. And this is a graph that has a fairly low density of information in it. So can you tell, it doesn't say it explicitly, but can you tell how many data points go into this graph? So for the top panel, can you guess how many there are there? Probably 6? Okay, why do you say 6?
Because they're like 3 lines.
Okay, because they're straight lines, and so usually if this were real data, you might see some variation even if it were just plotted with lines. So yeah, and also you note that it only has these 3 labels on it. Well, it also has this one. But yeah, I mean, it looks like there are just 2 data points there, 2 data points here, and 2 data points there. So 6 there. Another 6 here. Here it looks like there might only be 4 data points. There might only be these data points and these data points. So oftentimes you can sort of get a sense by sort of looking at a graph and thinking about sort of what might be behind it of exactly where the data are, even if it's a little bit obscured in the actual representation of the graph. So this is an example where this is a fairly large figure. There are 3 panels, but it looks like there are only 16 data points represented in this entire graphic. So a fairly low amount of information relative to sort of the amount of lines and everything that's sort of going on in the graph. So you could probably think about ways to redraw this graph maybe as a single panel instead of 3 panels, or potentially you might think about using a table in this case. But you can think about different options for displaying information that might do a better job than this does, for example. Let's see. Here's a good example of, thinking about scaling. So this sort of comes up all the time. You'll see a graph, and basically half of the data here is really obscured, and you can't really tell what's going on because of the fact that the scaling of I guess this is public school attendance or something like that, or number of public schools, because the number of public schools so outweighs the number of private ones that you can't really tell, what's going on in terms of the change over time in terms of the private schools. So this is if the point of this is that half of the data here are private schools and half are public, this is not doing a very good job of representing half of the data in this particular plot. In this case, it might be a little bit hard to display this all on one graph because of that difference in scaling. Actually, can anybody think of a way to get all of these, these data on a single graph, but to do it in a way where we can see the private school stuff better? Yeah.
Could you do side-by-side bars and like a second scale?
So where would you put the second scale on the right-hand side? Yeah, so that would be one possibility. There might be others, but you might be able to do it as basically sort of public school and then private school, but have the private school axis be over here and plot that on the other side. So that might be a good way to do it. Possible downside of that is it might make it a little less clear sort of what the relative magnitude of the public and private schools is, and somebody looking at it from sort of the 30,000 foot view might look at it and say, oh, private schools are about as common as public schools, which is not the case. So there are going to be trade-offs when you're doing these sorts of things. I guess you could also do a separate panel potentially, although that would sort of reduce that would be sort of a relatively little amount of data per panel in that case. Here's one I particularly like. So this is, this obviously still looks old, and these days this would be in color, and et cetera, et cetera. But how many data points are on this graph to the left here? If it's hard to see, it might be because there's all of this other stuff going on in the graph. Okay, so what 4 do you see?
The 3 for Japan and 1 for US or something?
Okay, so there seems like there are these 3 numbers that somehow relate to Japan. For those of you at the back might, I guess it says Japan up there. I was going to say it's hard to see the Japanese here. Well, okay, so there are these 3 numbers, and you start looking at this, and then you see the US flag in the background, and you say, well, maybe there's some data on the US here. I'll pick on Dustin a slight bit here, which is to say, I don't actually see a 4th data point there, but he was deceived in thinking, but rightfully so, sort of deceived in a way that the graphic led us to. Like, I don't think there's any data back here, but the graphic sort of makes it look like maybe there should be data back there. So I don't think that was, I think that's more the fault of the graphic than it is of us in looking at the graphic. I think this is just numbers for Japan relative to the United States. So it's something about productivity, U.S. output in person hour in manufacturing. And it says estimated per man hour in Japanese manufacturing as a percentage of U.S. output. So this is Japanese numbers relative to the U.S. There are 3 ratios here: the 44%, the 60%, the 70%. This is 70%, but because they've injected this extra unnecessary 3rd dimension here, this 70% really sort of lines up here with the 70% here, because this is supposed to be one of these 3D bars that's coming out of the page at you. Really for no purpose at all here, except to try and make it look sort of snazzy in some way. And then it's trying to, I guess, make this point of relative to the U.S. by putting the U.S. flag in the background, but then it makes it look like there's data back there, like there's sort of more going on than there actually is. So this is what some people who work with graphics a lot call chart junk, because there's just a lot of sort of crap in there that has nothing to do with actually representing the information. Any other questions or comments about that one? Another thing to be aware of is when you're making graphs, there's a reason that people do this, but it's also deceptive. This where they've taken the y-axis here and put in this little discontinuity here. So this is in thousands of schools. I guess this article had a lot of data from schools. This is a number of private elementary schools, and it's supposed to be, I guess, illustrating the fact that private schools in the U.S. have grown a lot over time. Again, this is old data, but when you look at this, it's like, oh wow, this is like increased by like 10 times the amount. Until you look carefully at the discontinuity here and realize this is going from 9 to 14 or 15, which is still a big increase, but maybe not as big as you might have expected if you don't see the discontinuity and say, oh, that's 0, that's 15. That's an order of magnitude increase, for example. Here's a sort of nice example of another of violating another principle of making graphs. So what do people notice about this graph that we might improve upon? I guess the caption is going to already tells us something about what the author thinks about this. So it looks like the left panel has exports in the sort of the line and imports in the dark black. But then on the right-hand side, they change the theme, the context or the theme of the graph, and they have exports in black and the imports in the white line, which makes it a little bit, makes it much more difficult to compare across the graphs. And yet, presumably one of the big points of a graph like this is indeed comparing between what U.S. trade with China is like compared with what U.S. trade with Taiwan is like. So in a lot of these graphs where you have multiple panels, you generally want to have basically everything about the design of the panels be the same from one panel to the next as much as you can. And that's going to make it easier on the viewer when they're looking at it to be able to interpret from one panel to the next. And otherwise, you make the viewer have to do a lot of cognitive work as they're going from one panel to the next to realize what's, in addition to what is being displayed and how that's changing in terms of the data. Then they also have to do all the cognitive work of trying to figure out, well, what's different in terms of how things are being displayed. And another thing that whenever I'm working with people who are showing me graphs, is something that I say I feel like every week or so is people often will make panels like this where the scale of the axes is different. And occasionally there may be a good reason to do that, but oftentimes you, in general, you want to try and make the scales of your axes be exactly the same. And so that's another thing to keep in mind when you're making plots that look like this. I don't think there are too many more. Oh, this one illustrates another principle here. So this figure is trying to say something about inflation over time. So it's saying how much is a dollar worth during President Eisenhower's term, which was terms which were in the 1950s, relative to how much is a dollar worth during Jimmy Carter's presidency during the late 1970s. And it's showing it, it's trying to be snazzy and attract the reader's attention by showing it as dollar bills that are changing in size. But one of the principles that people who have studied graphics and visualization have realized about how we as human beings perceive these things is that it's often difficult for us to actually think about relative areas and relative volumes. And so it's I think what's going on here is they're basically changing the length of the dollar bill from this. So think of that as a single unit of length, and they're basically changing it to be 44% as long here because they're saying that the dollar is worth 44 cents. That because of inflation, the dollar in 1978 is only worth 44 cents of what it was in 1958. But when the reader looks at this, one of the things that their eye is going to perceive is the change in area, maybe more so than the change in length. And so when you then look at the Carter dollar bill, it's more like maybe 1/10 or 1/8 the size of the dollar bill up top. So it makes it hard for the viewer to actually get a real sense of what the relative sizes of these numbers are when you do it like that. So in this case, the author's suggestion of how to plot this would just be to actually make it into a graph where you actually have this unit of purchasing power, and then you just show how that decreases over time. And that this is a much better representation than that, although it's not as flashy perhaps. Yeah, I think most of these illustrate similar things. This right one here has a pretty funny thing in here. This is presumably something that was, well, yeah, this is a graph from the New York Post, and it's trying to show the New York Post readership increasing to approach that of the whatever the news is. I'm not sure, probably the Daily News in New York City. You can see they've gotten up to 700,000 relative to 1.5 million, but they look really close together because they've conveniently hidden in here that they've changed the scale. So 500, 600, 700, 800, 1.5 million, 1.6 million. That I think is this is probably particularly egregious and deceptive to have done that and not even indicate any discontinuity. But given that this is not any sort of scientific graph, I suppose maybe not too surprising. Here's a good one. You see if you can see what the so the caption says something about changing the scale in mid-axis on this left-hand side one. See if you see what they mean by changing the scale in mid-axis and why it's so deceptive in this case. So usually the discontinuities that people put in are on the y-axis, but it took me a little while to see this even after I read the caption. But if you look at this, what you'll see is actually that it sort of looks like they were saying about exponential versus linear growth. This sort of looks like a linear change over time until you actually focus in and realize that the time scaling here is changing. So here's a gap of 8, a gap of 4, a gap of 4, a gap of 4, a gap of 8, a gap of 2, a gap of 3, a gap of 2, a gap of 1, a gap of 1, a gap of 1, a gap of 1. So there's a particularly bad way to represent time on a not only, yes, it's not even sort of changing in any sort of continuous way. It's sort of changing in this weird, in these weird steps. All right, so I think I will. I'll leave that at that. If you're interested, there are some other examples in here. Oh, actually, let me say this last one here. Show you this last one here. So this is illustrating. This is supposed to be illustrating life expectancy at birth for a variety of different countries for both men in the straight up and down hashing and women in the sort of diagonal hashing here. So if you're looking at this graph in this way, what do you take away as sort of the main points of showing these data here? I guess I should shift it up so you can actually see the y-axis. Okay, so this is years of life expectancy, basically from 50 up through 80 here. So if you were looking at this graph, what do you think is sort of what do you think are the interesting things that come out of this graph?
Females have longer life expectancy in all the countries by
Okay,
5
so
to 10 years.
yeah, so one of the big things is just the female to male differential in life expectancy. Anything else?
Because of the discontinuity in the scale, it looks like it's a huge percentage difference.
Okay, right. So you could critique this again. This question of sort of relative versus absolute differences and whether the discontinuity in the scale affects our interpretation there. Anything else? So how easy is it to see the differences between the countries and which countries have the largest and the highest and lowest life expectancies? I mean, I don't. It's probably maybe not too hard to see that the Soviet Union, USSR, again these are old data, has the lowest life expectancy for men because it's sort of, you can see there's that big, relatively big difference here versus these. But it's a little bit hard even with that to see it pop out because of the fact that we've got the men and women both in there on this same plot, and also because of the fact that it's just ordered alphabetically, and so there's nothing that really draws out what the ordering of the countries is in life expectancy. So if the purpose of this graph is for me to be able to go in and say, I want to know what the life expectancy was in Japan for men and women, well then it makes it easy for me to find Japan because it's alphabetized and it's sort of a way to look up data if that were the purpose of it. But usually the purpose of a graph like this is actually to emphasize differences and ordering and things like that. And if you order by something like alphabetization, that doesn't really do very much for us here in terms of actually seeing the interesting features of the data. So there are lots of ways I'm sure you could imagine to change this plot around. This is probably not how I would have done it, but the way that the author of this particular paper did it was to do it as it's not exactly a stem and leaf plot, but has a sort of somewhat of a feel of that. So they basically put men and women on separate sides, so you can really see the difference between women and men, which was one of the things that was obvious in the original graph. But then they order the countries and put them on this sort of ordered scale. So then when you look at this, then it's really obvious that the USSR is the lowest in men, still the lowest amongst women, tied with Germany, although not as big a disparity as it was for men. But we can see much more clearly that, say, Sweden is out in front both for men and women in this case, and that the other ones cluster in a way that wouldn't have been as easy to see in the other representation. Okay, so any other comments or questions folks have? Okay, so those were sort of some simple examples, but I think illustrate some of the themes of things to think about when you're thinking about designing a graph or interpreting one. So I have a few things to say about graphics in R. There's a lot more information in this unit, as I've mentioned in the notes that I've put up here, than we're going to have time to go through. I'm not going to say too much about, so one of the things about graphics in R is there are a bunch of different ways to do things, which is sort of the blessing and the curse of R in general, is there's always 4 different ways to do things. So the base R graphics, which come in the graphics package, which is loaded into R by default, you guys have, in various contexts, probably used a lot of the functions in those base graphics. You can basically sort of do anything, most of the things that you might want to do there, but sometimes it takes a lot of fiddling to get the aspect ratio right, or to put all the things in the position, all the pieces in the positions that you want. So there's often a lot of fiddling with things. I have some details on some tips and tricks in here if you're interested in looking through that on your own. I'll mention a few of the settings that I find particularly useful when I'm manipulating plots that have multiple panels. So 3 of them that I use all the time are MAI, MGP, and OMI, which you'll generally set with the par command. So MAI is going to manipulate the inner margins of subplots. So if you think about, I tried to just sort of lay out what some of the graphics parameters were here on the board. So if you just have a simple plot like this, MAI is going to be a vector of 4 values that basically say the size here, the size here, the size here, and the size here. And if it's MAI, it's in units of inches, and MAR is in units of text, which is basically sort of lines of text in a way that looks like this. So I often will set MAI to be something like this when I'm manipulating the spacing. And I'm often manipulating this because depending on whether I have text here, 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 or here, I'm often trying to get rid of a lot of extraneous white space when I'm making a plot that has multiple panels like this. So that's why I'm often going in and manipulating this MAI parameter. And then MGP will basically affect sort of where the text of an axis label is positioned and where the tick marks are positioned relative to the axis. And so sometimes I sort of try and again reduce down some extraneous white space by changing what the MGP parameter is, and that's what controls the spacing of text relative to the axis and tick marks relative to the axis. And then you can also manipulate the outer margin. So the analog to MAI, which controls the margin for an individual plot or a subplot within a multi-plot panel. So there's also, MAI will also control the sizing around each of the subplots. But you can also control the outer margins with, there's an OMI analogous value that's analogous to MAI. So I often am manipulating OMI, and then I may put an overall x-axis legend here, or an overall y-axis legend here, or an overall title for the plot there. So those are sort of the ones that I find most useful. I don't often end up manipulating this, but occasionally it might come in handy to know that there are these vectors that are too long that control sort of the size like this, that are called, there's FIN, which controls the x size and the y size, and then PIN controls the x size and the y size of the actual plotting region within the subplot, which is within the subpanel, and then DIN controls the overall sizing for the entire, I think this stands for device. So I think that's all I'll say about that. There's obviously a ton of different details in here that if you do help on par on the PAR command, that sort of gives you a whole laundry list of things that, that you have control over. Okay, so any questions about that? All right, so I thought I'd close by just showing some examples of plots from some of the sort of higher level graphics packages. So base graphics was sort of and the graphics package came along sort of early on in the development of R, and more recently there have been the development of some additional packages that make it easier on the user and control a lot of the sort of the sort of details of the graph, that control a lot of those for you behind the scenes and have a lot of nice defaults built in. So those are the Lattice graphics and a package called Ggplot 2 or Ggplot. So let me go to that. So both of these are quite nice for making pretty nice looking graphics without having to do a lot of monkeying with setting of sort of sizes and dimensions of aspects of the plot. So one of the main things to think about in terms of making graphics in either the Lattice or the Ggplot 2 context is sort of the basic motifs of ways, the kinds of relationships that we can represent with a graphic. And so the basic ones are basically these 5, that if you just have a single variable, you're thinking about representing something as just sort of the distribution of the variable, sort of like a histogram or a density plot. If you that this represents looking at the relationship between x and y, where you consider y as some sort of function of x. Here you've got y as a function of x conditioning on different levels of a, so often this will be in the manner of having different subplots for the different levels of the a variable, or potentially in a single plot having different colors or different line styles representing the different levels of the a variable. And you could extend that in some cases to have different levels of combinations of levels of an a variable and a b variable. And then the third one is trying to represent a 3D relationship of z as some function of the variables x and y. So what I'm going to show you in the examples is basically just how Lattice and Ggplot handle these various different kinds of plots. And this encompasses a number of, many of the different kinds of the different plots that you might want to make in actual practice. Okay, so those of you who were at the R bootcamp in August will notice that this looks familiar because I'm using the same data set that we used there. It's this comparative political data set. And it basically has time series data on a bunch of different variables for individual countries, for about 20 different countries, the OECD group of industrialized countries. So the variables are, there's a V-turn variable, which is the voter turnout in the country, real GDP growth in the country. The outlays variable is government spending as a percentage of GDP, and then there's unemployment rate, UNEMP. So we'll see some plotting of some of those variables. And then the other thing I should mention about both Lattice and Ggplot 2 is they work by basically layering information on top of a plot. And so you're basically building up a plot by applying sequentially applying different pieces to the plot. So it's good to sort of know that that's what it's doing. And then basically what's happening is you're building up an object. You're sort of adding to an object that gets more and more information embedded within it. And then at the end of the day, either explicitly or often implicitly, what happens is you're actually applying a print method to that object. And the print method, we've talked about S3 and S4 print methods. The print method in this case for these kinds of object is to actually create the plot. So that's sort of the framework of what's going on behind the scenes here. So for Ggplot2, the basic syntax, when you sort of first encounter it, it looks very confusing, but I think after you use it for a little while, it gets to feel more natural, and as long as you sort of see the theme of what's going on, I think that can help some. Is the basic command is you call the Ggplot function, which is in the Ggplot2 package, and you say what the data set is. So this is going to generally be a data frame. There's nothing in there now, but you would generally indicate a data frame. And then it has this aesthetic argument, AES, and that basically is where you tell it what the x, y, and potentially the z variables are. So in that sort of those 5 categories that I mentioned before, that's what the sort of the x, y, and the z here. And there may be options in here as well. And then you do plus, and you'll notice this parenthesis finishes off this call to Ggplot. So this is the nature, the manner in which we're basically adding together different pieces of the plot. And to go back to object-oriented programming in R, what are we doing here? We're doing plus on these plot objects, and so they've overridden the plus operator to have it mean something in the context of doing the graphic. So you're basically taking the object that's the output of doing Ggplot, adding that object to the object that's created by whatever these subsequent calls are that are layering the additional information on top of the plot. So this is just sort of a schematic of what it looks like, and we'll see it in actual. We'll see it actually here. So I guess I'll switch to R itself. Okay, so I'm just going to read in the data. For the moment, I'm just going to subset it to the US for this particular plot. But here we'll see an example of this idea of layering stuff on. So we're first going to call Ggplot and tell it that we want to plot voter turnout as a function of year. So that's this aesthetic and defining the x and the y variables. And then what do we say? Well, what kind of plot do we want to make? Well, that comes in the second call where we add on this layer that produces the actual plots. And so we say geometry point, that does the plotting of points, and we tell it to do it in black, in a black color. And then we can layer on another set of points, in this case the red dots, by calling geometry point again and adding that to the output from the object that resulted from the initial addition. And in this case, we say, well, now we're going to add, now we're going to again pass in the data and the aesthetic arguments because we want to redefine what the y value is for these points. And now we say we want to do those points in red. So that's how, in this case, we ended up with both the black points and the red points on the same plot, was basically by putting these different layers on. And presumably, if you were actually making this graphic for real, you'd want to then go and figure out how to add on an axis on the right-hand side that would be an axis relevant for the red dots, because this axis is relevant for the black dots. Okay, any questions so far? Okay, here's another example that will also show how to put multiple plots on a panel in Ggplot. So for that, I need this grid extra package. I'll mention that both the Lattice package and the Ggplot2 package are built upon this sort of underlying lower level package called grid. And apparently there's this grid extra that sort of expands upon that. Okay, so in this case, I'm just going to make up some data, and the whole point of this is to show how you might put some error bars on a plot. So this is just pretending that I have, say, a clinical trial where I have a control group and then a 1x group and a 2x group, whatever that means, 1 times the amount of drug and 2 times the amount of drug. But I'm just making up some data here. And so what am I doing here? Well, I'm creating an initial object, which is this figure 1 object. And if I printed that, I would create a plot that has the plotting from whatever I put in as the initial layers of the plot. So here I'm defining my x and y variables and the aesthetic argument, and now I'm saying to use a bar plot. And I'm giving some information about positioning, and I don't actually know what all of the details of all this means. The fill presumably means what color to use to fill in the bars. And then I'm adding to that another layer, which is to put in the error bars. And so there's a geometry error bar function that will do that, where I can again tell it, in this case I need to tell it sort of what's the upper point and the lower point of the error bars. So that's what this y min and the y max is. And then the width is basically just controlling how wide the error bars are. And then on top of that, I'm going to add a title, which I do with this ggtitle function. So at the end of the day, after I've done that, I've created this figure 1, but I haven't actually printed or plotted it yet. If I just typed figure 1, then it will actually print out the figure, and you can see that it's indeed produced the bars, it's produced the error bars, and it's produced the title, which were the different components that I added together. But then I can do things like this. I can take my figure 1 object and I can add to it, right? Because this is just object orientation in R. And so what I'm going to do in this case, what I'm actually doing here is sort of removing stuff from it. So I'm changing the theme, the background theme. So Ggplot by default has this gray in the background, and maybe you might think that additional color is not necessary. Maybe you don't want to print all that ink if you're making a lot of paper copies. This guy, Edward Tufte, who's very well known in the graphics community, suggests not including a lot of that sort of extraneous stuff. So maybe if you want to follow his principles, maybe you want to take that out. And you can do that by adding these additional calls onto the original figure. And the result of that is now creating the second figure, this figure 2 object. So I've now created figure 1 and figure 2. I have these 2 objects sitting around, and the idea is, okay, I can now take those objects and pass them into another function that will arrange them as a multi-panel plot. So that's what this grid arrange does, and that's why I needed to load in the grid extra package, was to get this grid arrange function. So this says, okay, just take these 2 objects, which represent plots, and plot them as a 1-row, 2-column representation. So if I do that, I get something that looks like that. So you could decide for yourself which of these sort of themes you like better, but that sort of illustrates a few of the some of the different things that you can do with this kind of plotting. Okay, so now let me just show you a few examples. So that was all Ggplot so far, what I've shown you. Now I'm just going to show you sort of side by side what you could do with the Lattice package and what you can do with Ggplot for some of those 5 different kinds of plots that I had mentioned. So Ggplot is generally somewhat more in the nature of having a single call to a single function, whereas Lattice is more in the nature of having a single call to a single function, although you can sort of add stuff on. Whereas Ggplot is this idea of adding together these objects. And Ggplot will generally, Lattice will generally use sort of the sort of notation that you would see, formulas you would see, like if you were using LM or GLM. So the tilde, you sort of recognize that from using LM, except in this case there's nothing on the left-hand side because we're just doing a density kind of plot. So if you wanted to do a density plot in Lattice, it would look like this. You call density plot, you tell it tilde v turn. If you want to look at voter turnout, you give it the data set, and then it'll produce something that looks like that. So that's what that looks like. Pretty nice looking graphic. You might want to tweak some things, maybe make the labels bigger and whatnot, but it does a pretty nice job just off the bat. And if you wanted to do this in Ggplot, this is the analog of what Ggplot will produce, and you can see some of the same sorts of things as we've already seen. You're adding to the base Ggplot, you're adding this geom density that does the density plotting, and then you're adding in some information about the X label. If we want to look at scatter plots, in Lattice that's XY plot, and in Ggplot again it's this idea of taking the base plot and then adding in this case a geom point call and a geom line call that will add in the points and the lines into the plot. So here we use this LM-like notation to do voter turnout as a function of year, and that'll produce something that looks like that. And in Ggplot, what we see is here we've put both the points and the lines in by making these 2 successive additions to the original plot. And you can see you can do subsetting just within the context of doing the plotting here as an additional argument to in either of these contexts. Okay, any questions so far? And then one of the nice things that both of these packages do is they deal with these conditioning plots really nicely. In Ggplot, this is called faceting. So if you want to do y as a function of x conditioning or given levels of another variable, for example, the country variable here, you can do it with the condition bar. And so we've got this sort of notation here. So this is going to plot a separate subpanel for each of the countries, looking at voter turnout as a function of year. So that will produce something that looks like that, which is pretty nice. It does a lot of nice layout for you and deals with sort of making the axes consistent across the different plots. And you can do something similar in Ggplot, except you have to call this Facet wrap function, and have to give this tilde country argument, which is sort of a different syntax than we'd seen for Lattice. And so if you did that one, that's going to produce something similar, but with sort of somewhat different way of doing the formatting. So this is a little bit scrunched given the size of my window here, but you can imagine this would look nicer if you had the ability to show this a little bit larger. And then also just an illustration here that you could, instead of doing this as multiple panels, you could do this as different colors or different line types for the different countries. So I'm just going to subset to a smaller subset of countries so that my single plot doesn't get too busy. But here I'm going to use Ggplot to plot voter turnout as a function of year, but have the color be different countries all in a single plot. So I have to leave the color argument empty for the moment. And then when I add the geometry line argument, that's where I then say, oh, different colors should distinguish different countries. So if I do something like that, oh, okay, so I guess I'm again going to make two different plots here. So here I'm distinguishing between countries based on the line type as opposed to based on the color. So I'm going to create the two objects, then I'm going to arrange them in a grid, and you can see that this is what you get. So that can look. That can be a pretty effective way of representing different conditioning on a stratifying variable. Okay, and then maybe the last thing I'll just show what a contour plot would look like, or what an image plot would look like, where you're trying to show 3 dimensions, but to do it in a plot without having a lot of sort of stuff sort of flying out of the plot, which is often not a very effective way to do it. So this is sort of funny data. This is basically a map of the height of a mountain or a volcano. So you have to define what the x and the y variables are, and then you can use, from Lattice, you can use the contour plot by using this, again, this sort of LM-like notation. Whoops. And that'll produce something that, oh, did I not run that? Maybe not. Oh, okay. All right, so maybe I can do this quickly on the fly. I think it's a reshape or reshape 2. Okay, so you get a plot that looks like that, which can be a nice way of representing 3-dimensional variables. And this would be the Ggplot representation of it. And if you want to do it as sort of solid colors instead of contour lines, then either level plot or this geometry tile addition in Ggplot would do it. So you can make a plot that looks like that. I tend to like these kinds of plots for doing 3 dimensions. And there's the Ggplot analog with not particularly nice colors, but you could monkey with that as well. Okay, so I think I will quit there. This is our last class. I will probably see some of you with questions on the projects. I'm going to send out some final sort of guidelines on exact submission of the projects for next Friday. I'll send it out in the next couple days. I hope you've gotten something out of the class and it's been worth your time. And I want to thank all of you particularly who've contributed both in class by asking questions and answering questions and on the bulletin board. So thanks. Oh, and I have solutions for problem set 5 up here as well.